We're doing electric fields today. So another hooray, no math. So for those of you in my class, the quiz is 1 week from today or 2 lessons away. So basically we have electric fields now, then electric field force in the next one, lab 2 lessons from now, and then the quiz. That's it. So this is really next to last thing we're gonna learn, and I'm gonna skip over the do now, just because. So we're gonna go into the distance between a proton and an electron is 5.3 times 10 to the negative 11th meter. So it's really impossibly small distance. So I want you to find both the gravitational force and the electrostatic force between these two particles. And you can do this. The mass of the proton, mass of electron is all in the reference table. So again, very small distance, very small masses. This is ME, this is mass of proton. And when you do the math, I'm hoping you did, you're going to see that the force of gravity between these two are so tiny, and the electrostatic force, it's small, but that force is so many magnitudes of force stronger. So we say the gravitational force is negligible compared to the electrostatic force. So basically that is important, because when you think about when we're walking around, we're actually not pushing through other atoms. The electro force is pushing us up. So here's a video, and I'm just gonna skip these. You can watch them if you go through the slides online. So neutral objects are attracted to charged objects, and that's through polarization, because the electrons can move a little bit within these. So for you, those of you in my class, remember when I ripped up the little pieces of paper and I put them on the desk, and I brought the charged tape nearby, those pieces of paper flew up and went to the tape. So you can't, and that's through polarization. And then also the same thing with comb. So how do these charges feel each other? There must be some sort of push or pull, which we call force, and that push or pull is this electric field. The electric field idea assumes a charge changes the space around it, and a second charge interacts with that space. So if you could visualize the electric fields, which are what these pictures are supposed to be showing, there's this area of influence all around the charge. Even though you can't see it, it's just there's these field lines that are there. And every charge has a field, or other charges interact with those fields. So the E field is a vector quantity. So do you remember what a vector quantity is? It means magnitude and direction. And direction. And we draw E field lines using vectors. So if you can see in here, there's little arrows. So to gather information about a field, we use what we call the positive test charge, and the reaction it goes tells us about the strength and the direction. So do you remember, if we have a positive test charge right here, where is it going to go? Oh, right there. Oof, that didn't come out right. I apologize. It looks better in my PowerPoint. So basically, if you put a positive test charge here, it's going to go out like in all directions away. It doesn't want to be near this positive charge. And same here. If you have a negative charge, it wants to go towards this negatively charged sphere. It would be like the same in all directions. So field lines point away from positive objects and in towards negatively charged objects. these arrows are not working in this one. Okay, so on your piece of paper, you should have rules for drawing E-fields, and very important, E-field lines point out of a positive charge, which we have here, and into a negative charge. So that's what I was trying to draw on that last page. It was quite messy. So positive to negative. You just gotta ask yourself, where is the positive test charge gonna go? And the closer the lines are to each other, the stronger the field is. So if you look in close here, these are pretty close to each other, these between these lines, but as you get further away, there's much distance. So that should make sense. Like the further you are from a charge, the less force you'll feel. Also, the more lines you have, here you can see there's way more lines. There's 1, 2, 3, 4, 5, I don't know. Up top there's 8 lines. Down here I have twice as many. So I know that this is a stronger field. A bunch more lines closer together, much stronger field. There is no field inside of a conductor. So if you remember the Van de Graaff generator, that sphere, within inside that sphere there is actually no electric field. The electric field is outside. And then number 4, all field lines start perpendicular to the surface of the object. So whenever we have that circle, you don't have anything like that. No, that just doesn't work. It has to go straight out. Always straight out. Like my little son here. Alright. Whatever. And then number 5, field lines never cross. So sometimes you may even see a Regents one saying which of these is possible, and if you see something that looks like that, you know it's not it, because that field lines can never cross. So on your sheet, there's going to be some examples, and actually I think I'm just going to skip. Well, I'll go to that. So we have a positive and a negative charge. So we know if you have a positive, near positive, it wants to go away, right? It does not want to be there. Actually, I think I'll just let the, yeah, so hopefully this works. And if you're in a positive test charge near a negative object, it wants to go to it. So if you kind of morph these together, there you go. There's your electric field lines around a positive and negative charge. In fact, I'll even add a couple more, but like this is going in, going in. In fact, I like to put arrows. This should have arrows, like so. But that's me getting picky. So remember, always positive to negative. What about two positives? What are you going to do there? Well, they don't want to be near each other, and they're going to bend away from each other. And actually, right here in the middle, 0 E field. There's no electric field right there in the middle. So this is a very common thing, actually, 2 parallel plates. You have positives on the top and negative on the bottom. How are your field lines going to go? Exactly like so. So positive straight down, and the electric, very important, the electric field strength is the same at any point between the plates where the lines are parallel. So here, 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 the electric field strength is the same. It's the same no matter where you are. So let's say, this is up and we have down, and I have a positive charge here and I have a negative charge here. Where would you put the polarity on the plates? Where would you put the positives and the negatives to make these guys float? Let me give you a second to think about it. If you want these charges to float, what would you do? So if you have positive charges here, they're going to repel this positive, and gravity is going to hold it down. So I have gravity, force of gravity, and then the electrostatic force is pushing that guy up. So negative, what do you think? Yeah, same thing. So again, the field lines still go positive to negative. So this Fe it is repelling from this negative, but the force of gravity is pulling it down. So there you go, making it float. So this is a quick one. I hope it makes sense. If you have questions, please let me know.